Hello everyone. In this lecture, we are going to illustrate the law of conservation of linear momentum in case of a system of variable mass. Whenever the mass of a system either increases or decreases with time, then such a system is known as a variable mass system. For instance, if a raindrop is falling under gravity, is collecting the mist it encounters and is continuously increasing its size and mass with time. Similarly, if the rocket is identified as a system, the mass of the system is continuously decreasing with time due to combustion of the fuel contains. The motion of such systems, that is, the system of variable masses, are explained by using the concept of impulse and momentum theorem and on the principle of conservation of linear momentum. If the external forces are acting on the system, then we use both impulse momentum theorem and also the law of conservation of linear momentum to explain the motion of such systems. If the external forces are not acting on the system, then we use only the principle of conservation of linear momentum to explain the motion of the system. Here, rocket propulsion is the best example for a system of variable mass where no external forces are acting and is explained on the basis of conservation of linear momentum. The rocket is experiencing the constant thrust due to the forceful ejection of gases, and hence it is accelerating upward or forward. Here, a rocket is a device used for carrying an artificial satellite to a suitable height for placing it in an orbit around the Earth or around a planet. A rocket consists of combustion chamber in which fuel is burnt. Due to the heat of combustion, the pressure inside the chamber becomes very high so that the rocket forces out a jet of hot gases from the tail, which acts as an action force. The jet of hot gases exerts reactional force on the rocket, which propels it upward. From the momentum point of view, the hot gases acquire momentum in the downward direction and the rocket acquires an equal amount of momentum in the upward direction. Here we are going to consider a single stage rocket to explain its motion and to derive an expression for its velocity. A single stage rocket is a launch vehicle that uses a single stage. All its fuel is burnt out in one stage and has only one booster to lift its payload to the desired altitude. Here in the diagram, we are observing a rocket of mass m moving with the initial velocity v. When the combustion process starts, the fuel inside the combustion chamber burns out and it starts ejecting the gases. The ejected gas has the mass of delta m. Due to the burning of fuel, there will be a loss in the mass of the rocket. Thus, after time delta t, the mass of the rocket will be m minus delta m and its velocity will be v plus delta V. Now, according to the law of conservation of linear momentum, the initial momentum of the rocket must be equal to the final momentum of the rocket after the time delta t. That is, Pi must be equal to Pf. Here Pi equal to mass of the rocket and the initial velocity v of the rocket, and Pf equal to the total momentum of the rocket and the momentum of the ejected gases. Here the momentum of the rocket after delta time, small interval of time, is m minus delta m into v plus delta v, and the momentum of the ejected gases is delta m v minus u is the momentum of the gases ejected. Here v minus u is the velocity of the gases ejected with respect to the ground or from the laboratory frame of reference. Thus we write Pi equal to Pf, that is momentum of the rocket before and after the time interval delta t. That is mv equal to m minus delta m into v plus delta v plus delta m into v minus u. So on solving, we are getting 0 equal to m into delta v minus delta m delta v minus u into delta m, which implies m into delta v equal to delta m delta v plus u into delta m. Since the term delta m into delta v is very small and hence it can be neglected, we write delta m into delta v is very small and hence we are going to neglect it. Then we write m into delta v equal to u into delta m, or we shall write delta v equal to u into delta m divided by delta v equal to u into delta m divided by m. If delta t tends to 0, then delta v equal to v dv and delta m equal to dm. Therefore, equation 1 will be dv equal to minus of u into dm by m. Here the negative sign implies that the mass is going to be decreased. At time t equal to 0, let us assume that velocity of the rocket is v0 and mass of the rocket is m0. And at time t equal to t, let it be v equal to v and m equal to m. Therefore, equation 2 can be written as integral v0 to v dv equal to minus of m0 to m u into dm by m. Implies v minus v0 equal to minus of u into log m minus log m0 equal to u into log m0 minus log m. Thus we shall write v equal to, that is velocity of the rocket equal to v0 plus u into log m0 minus log m, or it can be written as v equal to v0 plus u into log m0 divided by m. This is the expression for the velocity of the rocket at a given instant of time. The speed attained by the rocket when the whole fuel of the rocket is burnt out is called burnt out speed of the rocket and is the maximum speed that can be acquired by the rocket and is given by Vb equal to u into log m0 by mc. Here mc is the mass of the container. And one more thing, in the presence of gravitational force, V equal to, that is the velocity of the rocket, equal to V naught plus U into log m naught divided by mc minus gt. Here V naught is the velocity of the rocket at time t equal to 0 and U is the velocity of the gases ejected in the downward direction. So this is about the velocity of the rocket with the help of the law of conservation of linear momentum. Thank you.